Thank you to Planet Wild for supporting PBS. Take a look at this apple. Now look closer, and closer, and closer. When you see an apple, what you're really seeing is the light that's bouncing off the apple and into your eye. Some of the visible wavelengths of light get absorbed by the apple, and the leftovers enter your eye. And your brain says, I'm looking at a red apple. Now imagine for a second that you could zoom in on your vision beyond what a camera could do. You'd see little bacteria and fungi crawling around. Zoom in a bit more and you'll see all these densely packed red cells filled with water and sugar molecules. But keep zooming a bit more and you'd see nothing. Why can't we see any farther? All these molecules in the apple, and in fact, everything else that you see around you, are composed of atoms. But atoms are so small that visible light just wraps around them like an ocean wave engulfing a grain of sand. You're probably like, wait, I've used a microscope. Maybe you've seen images of what atoms and molecules look like. We've even split the atom. You'd think we've actually seen one, but that's actually not the case. This is a paradox. If everything around us is ultimately made of atoms, but we can't see atoms, then how can we see anything? We're gonna take a trip into a very small world and find out just how weird that answer is. Hey smart people, Joe here. All right, first things first, we've already established that we can't see atoms with our eyes, so it's worth asking, how do we even know that they exist? Luckily, we have thousands of years of clues. The story starts with Greek philosopher Democritus. In the 4th century BCE, Democritus proposed that all matter is composed of tiny, eternal building blocks called atomos. That means uncuttable. And those invisible atoms were whirring about in an infinite void all across the universe, stacking together to form stuff. Honestly, not bad for nearly 2,500 years ago. But for most of human history, the atomist's view was condemned because most people sided with Aristotle. He thought that matter could be infinitely divided and was composed of just 4 elements: earth, fire, air, and water. Sounds like he was into Pokemon. Although in the East, some schools of Buddhism, Hinduism, and Islam had developed their own notion of indivisible atoms. Of course, none of these ancient thinkers had any way to measure or really even consider the world at that tiny scale. So this was really all more of a thought experiment to argue about, well, I don't know, wearing togas and drinking wine. But starting in the 1600s, atoms jumped from the realm of philosophy and religion into the world of science. That's when this guy first estimated how big an atom was. He measured how much incense had to be burned before it could be smelled across a big chapel, and he calculated how many incense particles he started with. And surprisingly, he wasn't that far off. Then, in the early 1800s, John Dalton realized that the chemicals in familiar liquids and gases, well, they always contain whole number ratios of different elements, like how water is always 2 parts hydrogen to 1 part oxygen, and not like 1.5 parts oxygen. This was proof that there must be some smallest unit of matter that acts like Lego building blocks to make all the stuff around us. A few decades later, we caught a glimpse of those Legos in action. In 1827, the botanist Robert Brown was looking at grains of pollen floating in a perfectly still puddle of water, and he noticed that they'd always jiggle randomly. And Albert Einstein later showed that the pollen's spontaneous little wiggling was actually caused by collisions with invisible water molecules. This meant that atoms were real physical objects. But what are those atoms actually like? In the 1890s, J.J. Thomson put some electricity in a vacuum tube, and he saw a stream of light stretch between the 2 ends. And he could bend that beam with magnets, which meant that even neutrally charged atoms must be made of some smaller bits, some of which are negatively charged, electrons. And Thomson proposed that those electrons were scattered around the atom like chocolate chips in a cookie. Well, that picture also turned out to be wrong, but it does sound delicious. Later, Ernest Rutherford shot tiny, positively charged particles at a sheet of gold, and he noticed that occasionally, instead of passing through, the particles bounced off. This showed that the atom has a dense, positively charged nucleus at the center, while the rest of it is mostly empty space. If an atom were the size of a baseball stadium, the nucleus would be about the size of a baseball. Okay, well, what about the electrons then? How do the chocolate chips get distributed if the cookie is mostly empty space? Niels Bohr proposed an idea in the early 1900s. He heated up hydrogen and he noticed that it gave off these distinct and predictable colors of light. So he drew a model where electrons live in these distinct tracks around the nucleus, like planets orbiting a star. And that's how we arrived at the emoji-friendly atomic model that we're all familiar with, which is also wrong. But we'll get back to that. So those experiments gave us a pretty good mental picture for how an atom should look. We just need to take a real picture of one and then see if it lines up, right? Not so fast. You see, the problem is atoms are really tiny. One atom is about as small compared to an apple as an apple is to the entire Earth. The smallest thing that a human eye can resolve is about 1/10 of a millimeter. That's about the width of a human hair. Visible light itself has a wavelength about 1,000 times smaller than that, a few hundred nanometers. That's about the size of a typical bacterium, like E. coli. But the diameter of a single atom is thousands of times smaller than visible light itself. Any light that we can see physically cannot bounce off of an atom, so it is forever invisible, no matter how far we zoom in. But what about all the light that we can't see? What about all the rest of the electromagnetic spectrum? In the 1890s, scientists accidentally discovered X-rays, a much higher energy form of light with a wavelength that's 10,000 times smaller than what we can see. That means it can pass straight through our skin and leave shadows of dense solid objects, like bones. A few decades later, scientists started taking X-rays of molecules too. This famous X-ray image taken by Rosalind Franklin in 1951, for example, that's what inspired the realization that DNA has its twisted double helix shape. But even X-rays are not small enough to see atoms. So scientists had to try something even smaller, electrons themselves. Remember these cool toys with all the pins? That is basically how an electron microscope works. It shoots a beam of electrons at something and it maps out the surface by looking at how those electrons bounce off or pass through. Electron microscopes can produce impressively creepy 3D images of very tiny objects and can even map out the rows of atoms in something like a crystal. But they still lack the resolution to make out individual atoms. To do that, we have to move from seeing to feeling. More advanced electron microscopes, they hover an ultra-thin charged needle over the material they're trying to see, kind of like a record player. By tracking how electrons in what you're trying to see tug or vibrate the tip, they can resolve individual bumps of atoms. By adding a little extra voltage, we can also drag individual atoms around. That's what allowed for this, the tiniest movie ever made. Then scientists figured out how to put individual atoms in a sort of trap. In 2018, this photo was taken using a normal digital camera. A strontium atom was trapped in an electric field, zapped with a laser, and they took a long exposure photo of the light that it radiated back. If you look in the very center, you'll see a pale blue dot floating in dark, empty space. Sorry, anytime I say pale blue dot, that voice just comes out. Well, that right there is an atom. Or is it? I mean, it's sort of like seeing the lights of a faraway car at night. I mean, you can't say you know what the car looks like. So have you really seen the car? That is something to fight about in the comments. And that brings us to this image. It's the most high-res shot we've got of atoms. It came from researchers at Cornell University in 2021. What they did was fire electrons at a material from different angles, and it recorded the way that they bounced off. Then they used fancy computer stuff to reconstruct where the atoms must have been to create that pattern, resulting in this image. So, does this count as seeing an atom? I mean, it sort of seems like being in a dark room and shooting a bunch of bullets at a sculpture. You can look at where the bullets landed and use that to paint a picture of the sculpture's shape, but have you actually seen the sculpture? I guess it depends on what you mean by see. A purist might say that seeing is capturing light with one's bare eyes. And in that case, we certainly have not seen an atom. If you count the use of fancy machines to magnify that light, then still no. But can we see something by feeling it? I mean, people with visual impairment can read Braille, and they can visualize the 3D structure of art pieces in tactile museum exhibits. Is that any less seeing than seeing with our eyes? I genuinely don't have the answer, but it does feel sort of different. But there's one more wrinkle when it comes to seeing an atom, and it's something that throws this whole quest kind of on its head. Remember Bohr's model of the atom? Well, it turns out that's also not how an atom works. See, in the last century, we've learned that atoms are actually much, much weirder than that. This is the realm of quantum mechanics, where everything you thought you knew about the world just goes right out the window. There's this famous experiment where scientists shoot single electrons at a screen with 2 little slits cut out. Shooting 1 electron at a time at the screen, you'd expect to see 2 little lines appearing on the wall behind it, right? But instead, what you actually see is a stripy pattern. That can only happen from each individual electron acting not like a particle, but like a rippling wave. It travels through both slits simultaneously, and then each wave interferes with itself. This is super weird. But what's even weirder, when you install a little detector to track which slit the electron passes through, you see a different pattern on the back wall. 2 distinct lines, as if the electrons were behaving like particles. How do we make sense of this? Well, physicists still aren't quite sure, to be honest. They've been debating this one for almost 100 years. So don't feel bad if your head hurts too. But they mostly agree that before an electron is measured, it doesn't actually have a position. It exists somewhere in a cloud. There's some probability that describes where it could be if you were to measure it, but that doesn't mean that it's actually there at any given moment. You can sort of visualize it like this, where each dot represents where the electrons might be measured. The more tightly the dots are packed, the more likely they are to be found in that place. Well, you notice how those probabilities end up forming orbit-like shapes. They're similar to the ones that we're used to seeing, but there's some really important differences from that old planet model, and they are very weird. In a way, an atom actually is and isn't mostly empty space. It's filled with this cloud of electron possibility. So what does this mean for our quest to see an atom? Well, to see something, you have to interact with it, whether that's bouncing light off of it or feeling its electrons. And quantum theory tells us that any time that we interact with an atom, that changes the way that the atom behaves. So what does the atom look like when we're not watching? That might be an impossible question to ask of the universe. We can't know. Okay, but that brings us back to that first question. If atoms are so strange and elusive, and if everything is made of atoms, then how can we see anything? I mean, if the bricks of the universe are invisible, how can we see the house? The answer is that seeing many atoms is very different than seeing a single atom. See, when atoms are clumped together into matter, their electrons interact with each other and they create this sort of interconnected electromagnetic ocean. When light hits the material, it bounces not off individual electrons on individual atoms, but off of that collective sea of electrons. When we look at an apple, and we're talking about some 10 million billion atoms, all connected in a web of chemical bonds. And collectively, they can reflect light. It's sort of like looking at an image on your computer screen. All the rich colors and contours that you see are actually composed of tiny individual red, green, and blue pixels. You can't make out the individual pixels, but you can see the bigger features that emerge from all of their collective light. Just like the images on your screen, the objects that we see in real life are just blurry averages of what's really underneath. We just have to accept that the world that we know and see is one that emerges from a world that we will never be able to observe directly. The deeper we look into an apple, the less we seem to see. But I mean, isn't seeing the unseeable what science is all about? It's sort of what being a human's all about. We may not have ever seen an atom, but we still know that they're there. We find ways to catch their ripples and shadows and textures. Eventually we build up so much information that we can predict with incredible accuracy what we're gonna see. I mean, compare this to, say, looking for Bigfoot. I haven't seen him either, so I can't say whether or not he exists. Maybe he's invisible. Maybe he lives in Antarctica. But if you brought me mounds of repeated evidence from different locations with no alternative explanation, so much that you could predict where Bigfoot's footprints will show up next, then, well, even I might start to buy it. That's exactly what we've done for atoms. We can't see them, but we still know them shockingly well, probably better than we know ourselves. By monitoring how often electrons in an atom change orbitals when we blast them with a laser, we construct clocks that can keep time for billions of years without losing a second. We can use the color of light given off as electrons change orbitals to figure out what makes up the atmosphere of planets orbiting other stars. You are made of atoms. Every cell in your eye that processes light is made of atoms. Your brain, which constructs the experience of seeing, is atoms. We are the universe's atoms trying to see ourselves and failing. That's a very strange thought and weirdly humbling. But if you look deeply enough at something even as simple as an apple, it may just open up an entire universe of secrets, or at least some very good questions. Stay curious. And thank you to Planet Wild for supporting PBS. Every month, their crowdfunding community of over 20,000 members funds a mission to bring back endangered species, protect oceans, and restore forests. All their missions are documented through video updates on YouTube and text reports on their app that show the kind of work the Planet Wild community supports and what impact it has. In one of their latest missions, they stopped plastic before it reaches the ocean with a simple yet effective solution. Joining the community is possible at any amount, and the first 100 people to sign up using code SMART5 will get their first month paid for. After that, it's possible to cancel anytime. To join, just click the link in the description, and that's also where you can check out their mission video about fighting ocean plastic. Thank you to everyone who supports this show on Patreon. Like these fine people at our top tier and many others that are part of the community that makes this show literally possible. We could not make videos like this without your support. If you like the science that we are bringing to the world and you'd like to see more of it, check out the link down in the description where you can learn more about supporting our show directly. Be Smart is a product of real, organic, curious human brains in an age of questionable AI science slop everywhere. If you'd like to see more content like this, definitely check out that link down in the description. I mean, I'd like to see an AI do this. Eat an apple, huh? Try that. Computer. You don't even know what apple tastes like. Play the movie. Boop, doop, 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 doop. Well, that's going in the end card. Great. All right.
Cut.
I'm not supposed to eat the apple.
No.
Right.